Physical quantities and units. A physical quantity consists of a magnitude or size and a unit. For example, it would be no good asking for a piece of carpet 3 by 2 without specifying whether you meant 3 meters by 2 meters, 3 yards by 2 yards, or some other unit of length. Another example, if you were offered payment of 5 for a job, whether you did the job would probably depend on whether the units were pounds or pence. To avoid confusion, the SI or System International has been adopted by scientists around the world. This consists of 6 base units. I'll list the units in this table. First we have mass, the unit is the kilogram, abbreviation kg, length, unit the meter, abbreviation m, time the second, with an s, temperature in the Kelvin, which is a capital K. Note that the abbreviations are a capital letter if the unit is named after a person, and a lowercase letter if they're not named after a person. Electric current is the ampere, capital A, and the amount of substance is the mole, abbreviation MOL. There are also derived units, which come from combinations of the base units. I'll run through a few examples by listing them in this table. First, velocity, which is in units of meters per second, abbreviated as ms to the -1, and that is already in base units of meters and seconds. Force is in units of the Newton. Note, even though this is named after Isaac Newton, in the word it gets a lowercase letter, in the abbreviation it gets an uppercase N. Now a Newton is a force that would give an acceleration of 1 meter per second squared to a mass of 1 kilogram. So the equivalent of a Newton in base units is a kilogram meter per second squared. Charge is measured in coulombs, abbreviation capital C, and that is equivalent to a current of 1 ampere flowing for 1 second. So a coulomb in base units would be an ampere second. Pressure is units of pascals, abbreviated to capital P lowercase a. Now Pascal is a Newton per square meter, and Newton previously we quoted as a kilogram meter per second squared, so the Pascal comes out as a kilogram meter to the -1 seconds to the -2. And the last example of energy with the unit of the joule, abbreviation capital J. Now a joule of work is done if 1 Newton moves through a distance of 1 meter, and therefore combining the newtons from up here we get that the joule in base units would be a kilogram meter squared seconds to the -2. When doing calculations, your data will often be given in non-SI units, such as centimeters, kilonewtons or megajoules. You must know what the prefixes mean and how to convert. So I'll run through a list of the prefixes you need to know. 10 to the -12 is known as pico, and the abbreviation is a lowercase p. We tend to go up in thousands, so 10 to the -9 is known as nano, abbreviation lowercase n. 10 to the -6 is micro, and that is the abbreviation of the Greek letter mu. 10 to the -3 you'll be familiar with as milli, abbreviation lowercase m. 10 to the -2, not following the trend of going up in thousands, is centi, as in centimeters, abbreviation lowercase c. Then we get on to multiplications. 10 to the 3 is kilo, abbreviation lowercase k. 10 to the 6 is mega, which has an uppercase m to distinguish it from milli with a lowercase m. Do be careful with these. 10 to the 9 is giga, which is uppercase G, and finally 10 to the 12 is tera, which is an uppercase T. When doing a calculation, convert to SI units before starting the calculation. Then your answer will be in SI units. You can always add a prefix to your answer if it's appropriate. Let's run through a very simple example. A snail travels 54 millimeters in 2 minutes. What is their average speed? Well, 54 millimeters is 54. The milli prefix means times 10 to the minus 3 meters. I'd be tempted to write my answer like this, rather than converting to standard form of 5.4 times 10 to the minus 2 meters. Your calculator will never get this wrong, whereas you probably will get it wrong occasionally, especially under the pressure of an exam. 2 minutes is 120 seconds. Now we can write down our formula. Speed is equal to change in distance over change in time, which is our distance of 54 times 10 to the minus 3 meters over 120 seconds, which comes out at 4.5 times 10 to the minus 4 meters per second. If appropriate, we could then say that that is 0.45 millimeters per second. Take great care when calculating areas and volumes. Here we have 1 square meter. Now a meter is 100 centimeters, and very often students will think that a square meter is 100 square centimeters. But a square meter is 100 centimeters by 100 centimeters. So the area will be 100 times 100, which is 10,000 square centimeters. In millimeters, it would be 1,000 millimeters by 1,000 millimeters. So the area in square millimeters is 1 million square millimeters. For volume, here we have 1 cubic meter, which is 100 centimeters by 100 centimeters by 100 centimeters, giving a volume of 1 million cubic centimeters, or 1 times 10 to the 9 cubic millimeters.